All right, welcome. Hope that you're staying. If you're just fast forwarding towards the end, then good luck. Happy hunting. So I have the limit as x goes to 3 of 2x minus 6 over x squared minus 5x plus 6. The first thing, as always, that you want to do is substitute what I am looking for into the function. When I do that, 2 times 3 is 6, minus 6 is 0. 3 squared is 9, minus 15 is negative 6, plus 6 is 0. So I got 0 over 0. Which is great. That means I can algebraically probably do something with this. I can notice that I can factor these. So I'm going to say this is 2 times x minus 3 and x minus 3, x minus 2. My x minus 3's cancel. So now this becomes the limit as x approaches 3 of 2 over x minus 2. At this point, I can now try and substitute the 3 in, and I get 2 over 3 minus 2, which gives me 2. So I know that the limit of this function is 2, but that the function does not exist at 3. So this is a hole in the graph again. Here, limit as x goes to 0 of x squared plus 2x over x squared plus 6x. Always substituting in first, I can see very clearly I get 0 over 0. So the function does not exist at 0, but the limit may still exist, may. I'm going to factor. I get x times x plus 2 and x times x plus 6. My x's cancel. And I substitute this 0 in. So I have 0 plus 2 over 0 plus 6, which gives me 2/6, which is 1/3. So again, the limit here is 1/3. However, the function does not exist. If I substitute in -1, I get 0 over 0. Don't always assume you get 0 over 0. You might get like 10, in which case the answer is 10. But I do get 0 over 0 here. I factor out a 2, so I have x plus 1 over x plus 1, x plus 1. Now this can only cancel with one of these. So this becomes the limit as x goes to -1, or x approaches -1, of 2 over x plus 1. That gives me 2 over -1 plus 1, which is 2 over 0, which is undefined. So the limit does not exist. So this is a case where I got 0 over 0. I was able to reduce something out, but it is still a limit that does not exist. And if you look at this graphically, what this looks like is at -1, there's not actually a hole like there was in these cases. There's a vertical asymptote. And I know that there's a vertical asymptote based off of this. That tells me vertical asymptote because I have some number divided by 0. And some number divided by 0 will be a vertical asymptote, as where 0 over 0 will typically be a hole. So this is sort of a unique case, but it is a case where you get 0 over 0 and still a limit that doesn't exist. All right, moving along, we have some of our rationalizing technique. Again, the first thing I'm going to do is substitute that in. I have √7 minus √7 over 0, which gives me 0 over 0. So I'm going to rationalize this. The conjugate of this is square root 7 minus x plus square root 7, and I'm multiplying that on top and bottom. Now, the rationalizing technique definitely takes more sort of like a space as opposed to the factoring. The factoring is usually a lot nicer. But square root 7 minus x times square root 7 minus x gives me 7 minus x. And negative root 7 times positive root 7 gives me -7. In the bottom, I have x times that whole denominator. Remember that you don't really want to multiply this out. Your goal is to cancel something in the numerator and denominator. So the numerator you're multiplying out to rationalize it. The denominator you don't need to rationalize. You want to leave it as factors. My 7 minus 7 cancels, and I'm left with -x over square root 7 minus x plus square root 7 times x, and my x over x can now cancel. So this becomes the limit as x approaches 0 of -1 over square root 7 minus x plus square root 7. And now when I evaluate this limit, I get negative 1 over square root 7 minus 0 plus square root 7, which gives me negative 1 over 2 root 7. And, if we wanted to rationalize from this point, you could say it's a negative root 7 over 14. All right, let's try 2 more examples of that. When I substitute in this 0, I'm just going to zoom in so that I have a little bit more space. Yeah, I know that you can't do that, but when I substitute this in, I'm going to have 0 over 0. So I multiply by the conjugate, square root x plus 1 plus 1, square root x plus 1 plus 1. In the numerator, that's going to give me x plus 1 minus 1. In the denominator, I'm not going to multiply that out, just x times square root x plus 1 plus 1. 1 minus 1 cancels. I'm left with x over x times square root x plus 1 plus 1. And x over x cancels. So this becomes the limit as x approaches 0 of 1 over square root x plus 1 plus 1. Now if I substitute 0 into this, I get 0 plus 1, which is 1, the square root of 1, which is 1, 1 plus 1, which is 2. So here I know that, again, because I got 0 over 0, the function does not exist at this point, but the limit does exist, and the limit is 1/2. So that is the y value that this graph is going towards as I get closer and closer and closer to 0. All right, if I substitute 9 and 3 minus the square root of 9 would give me 0. 9 minus 9 would give me 0. Function doesn't exist. Limit might. I'm going to multiply by the conjugate, 3 plus root x, 3 plus root x. I get 3 minus, nope, just kidding. 3 times 3 is not 3. I get 9 minus x over x minus 9 times 3 plus square root x. Now you might be looking at these and thinking, oh, I can cancel them, and you only sort of can, and I just want to show how that looks. What you have to do is factor a negative 1 out of this numerator so that the x becomes positive and the 9 becomes negative. That's a b. 3 plus root x. And now my x minus 9s can cancel. So this becomes the limit as x approaches 9 of negative 1 over 3 plus square root x. If I substitute 9 into this, the square root of 9 is 3. 3 plus 3 is 6. So the limit here is negative 1/6. And again, the limit existing and being equal to negative 1/6, but the function being undefined. This representing most likely a hole. Okay, so now we're going to look at some graphical ones. In this case, if I talked about the limit as x approaches 0 from the right of the function absolute value 2x over x, which I've already graphed for you, what I would get is 2. Because as I am moving from the right towards x being 0, oopsies, forgot that would happen. As I'm moving along here towards x being 0, here's x being 0, the y value of the function is 2. As I am moving from the left towards 0, the y value is negative 2. So I have the limit as x approaches 0 from the right being 2, and the limit as x approaches 0 from the left being negative 2. So overall, the limit as x goes to 0, that does not exist. Because the limit from the left must be equal to the limit from the right. And I got 2 and negative 2. So overall, my limit does not exist. Now, one that doesn't have that filled in. Find the limit as x approaches 1 of f of x. So I have this piecewise function, and I again have graphed it for you. You're welcome. If I talk about the limit as x approaches 1 from the right, so that means I want to start on the right of this function and keep moving along it towards x being 1 on the function. Now here's x being 1, so that would be right here. That y value is 3. The limit as x approaches 1 from the left, so I'm starting on the left of this function. I'm going towards the x value of 1, and that goes towards the y value of 3. Because these two limits are equal, my overall limit is equal, which is 3. Okay, all we have left now is this difference quotient. So welcome if you just joined us because you skipped all the way ahead. Very exciting, difference quotient. The difference quotient formula. The limit as h goes to 0 of f of x plus h minus f of x over h. Now, I'm just going to point out an extra thing. What this is, you may have heard this word from some of the wonderful students in Calc. This is really your formula for finding a derivative. And in AP Calc, we only spend like half of the entire school year talking about derivatives. And then we spend the other half doing derivatives backwards. So I guess we spend the whole year with this. So it's just like a little bit important. So there are 3 questions here, but they take a lot of space. So in your notes packet, I would try and find like a blank page, particularly at the end of the notes packet, because that's how pages work. That's where you would have a blank one, hopefully, depending on what year this is. So go look there, see if you have some extra space. I'm going to look at this first problem. Now remember that what f of x plus h says is that you are replacing x with x plus h. So if I'm doing this first thing, I'm taking this function and I'll have the limit as h goes to 0 of 3 minus 2. I'm replacing x with x plus h. And that just gives me the f of x plus h. All I've done is replaced x with x plus h. Now I need to subtract f of x. Well, this is what f of x is. And this is all over h. Now this question is actually a little bit different than how you guys did it in the beginning of the year, and the only difference being you didn't have this little piece in the front that said limit as h goes to 0. So I'm going to do this problem as if that's not there. I'm just going to like bring that back right at the end so that you can see what you used to do. So I need to FOIL these out. That becomes 3 minus 2 x squared plus 2xh plus h squared. Whoop, that's not a squared. Minus, and I'll just distribute this this negative. So negative 3, positive 2x squared. And this is all over h. Now I'll distribute this negative 2. 3 minus 2x squared minus 4xh minus 2h squared minus 3 plus 2x squared all over h. Now, what should always happen is this right side should cancel. So 3 minus 3, negative 2x squared, positive 2x squared. Looking at what I have left, I will factor an h out of that. So I'm left with negative 4x minus 2h over h. My h over h cancels, and I get negative 4x minus 2h. At this point, we stopped back in chapter 2. But now we're going to take it a step further, and we're going to say, hey, look, this limit was always here. What we want is the limit as h is approaching 0. I couldn't evaluate that in the beginning because that would be giving me 0 in the denominator and 0 in the numerator. If this was 0, I'd have f of x minus f of x. So if I substitute that 0 in for h now, this just becomes negative 4x. This is the derivative function. So we just found the derivative of 3 minus 2x squared. Now, if you're still thinking like, whoa, Mr. Dybus, what is a derivative? Hold on, we'll talk about that in section 11.3. I'll give you an actual, definition of it and everything like that. But for now, just know that that's what you just found. How cool. So I'm going to, just spy everything over there. Now I'm going to do this problem. So we have the limit as h is approaching 0 of, remember that I'm replacing x with x plus h, keeping everything else the same. So square root x plus h, and that plus 1 is hanging out in that square root as well, minus f of x, which is just the original function, all over h. Now I can't substitute 0 into this because once again I'll get 0 over 0. So now I have to use my rationalizing technique. There we go. So I'm going to multiply by x plus h plus 1 in a square root plus square root x plus 1. And I'm going to do that on top and bottom. This looks so long, and it is. It is very long. I told you, vengeance. It has a wrath. It's been so mad that you haven't been here. I'll stop. All right, so if I multiply these conjugates, I get x plus h plus 1. That's from these first trinomials multiplying. And then when these binomials multiply, I'll have negative x plus 1 all over h. So that becomes x plus h plus 1 minus x minus 1 over h. My x minus x cancels. My 1 minus 1 cancels. My h over h will cancel now, because that's all I have left. So this becomes the limit as h approaches 0 of 1. That's all I have here. So the limit as h approaches 0 of 1 is just 1. A very fun thing there. But what we just found was the derivative. All right, so moving along, we have one last question. And it's going to be a little bit mixed in here. Let's switch colors so that it becomes a little bit more clear. If I'm doing this one, I'm going to have the limit as h goes to 0 of 2 over x plus h minus 1. Again, I just replaced x with x plus h minus 2 over x minus 1, quantity all over h. So now, if I'm going to combine these, I'm going to have to get a common denominator between them. So I'm going to rewrite this and just have 2 over x plus h minus 1 minus 2 over x minus 1. Now this is all still over h. But for the sake of room, I'm going to multiply by x minus 1 and x minus 1. And I'm going to multiply by x plus h minus 1 and x plus h minus 1. I'm not going to multiply out the denominator. I'm hoping that something will cancel in some way. I don't know. I'm hoping. I will multiply out the numerators. So in this numerator, I will have 2x minus 2 over x minus 1, x plus h minus 1, minus, I'm multiplying out this one, 2x plus 2h minus 2 over, and again, that same thing, x minus 1, x plus h minus 1. Now remember that I am subtracting, so 2x minus 2x will cancel. Negative 2 minus negative 2 will cancel. So I'm left with just a negative 2h over x minus 1, x plus h minus 1. You might be thinking, well, wait a second. How is this, at all solved? Well, this over h is still here. And now we want the limit as h goes to 0. Well, wait. If I substitute 0 in, I still get 0 over 0. But this h over h can cancel. If you're thinking about why, just thought bubbles here. This is negative 2h over x minus 1, x plus h minus 1. And this is an h over 1. So when you're dividing by a fraction, you multiply by the reciprocal. So this is why our h and h are canceling. So now this becomes the limit as h approaches 0 of negative 2 over x minus 1, x plus h minus 1, which will give us negative 2 over x minus 1 times, if h is 0, this would just be an x minus 1 again. So that would give us negative 2 over x minus 1 squared. And again, this is my derivative. And we'll learn more about what the heck I'm talking about when I talk about that derivative when we get to section 11.3. All right, thanks for joining.